Yeah, one of the judges is.
Okay.
Alright, you may begin.
Over here.
My name's Opinder, Dhami,
My name is Arun, Kumar.
and we're both seniors here at San Jose State in the Biomedical Engineering program. We're doing our project on interfacial biomaterials for medical devices, and it's with NASA Ames Research Center located in Mountain View. Our industry advisor is Dr. Diana Gentry, and our SJSU advisor is Dr. Selvaduray. For our presentation outline, we'll be starting off with the biomedical motivation, moving on to the background, followed by FDA consideration, design of experiments, methods, results, conclusions, future works, and cost analysis.
So for biomedical motivation, we're interested in bone screws, which are medical devices used in the fixation of bone to treat fractures or other defects. They're commonly made out of metals or polymers. Current bone screws are effective, but they can have problems such as weakening the surrounding bone or leaving empty holes in the bone when they are removed or after they degrade in the body. And so materials for bone screws can potentially be enhanced by combining them with cell-secreted biological substances to form what we call interfacial biomaterials. So here's some background about what interfacial biomaterials are. So biomaterials are just synthetic or natural materials that are used in biological systems, commonly for a medical purpose. They can be made of metals, ceramics, or polymers. And interfacial biomaterials are unique because they use living cells which have the ability to self-assemble and replicate into microscale structures, and we use this interaction to form what's called the interfacial biomaterial. The concept's illustrated here. You start with a substrate, which is then seeded with cells, and then the cells secrete a biological substance that binds to the substrate, and then finally the cells are removed and you're left with the interfacial biomaterial, which is a combination of the two components. So for our literature review, we started looking at cells that we think would be potentially useful to form these materials. The first, so we came across Acetobacter xylanum, which is known to produce cellulose during fermentation. Bacterial cellulose resembles the extracellular matrix of bone, so it has been used in tissue engineering for bone, and it's also chemically purer than plant cellulose. We also researched some possible materials to use for substrates. The first one is PLA mixed with 15% hydroxyapatite, which is a mineral that's found in bone that promotes bioactivity and cell proliferation. When it was combined with PLA, which is a polymer, it also added a shape memory property to the new material formed, and it supported MSC growth, which are stem cells. PCl and PLA, a combination of the two polymers, was the other material we looked at. It has good cell adhesion and high strength, and by modifying the weight ratio of the two separate polymers, you can have it more hydrophilic or more mechanically strong. So the medical device that's most similar to the product that we want to make is the bone fixation screw. It's a class 2 medical device with product code HWC, and it's intended to aid the surgeon in the stabilization and fixation of smaller bones, typically in the hands, feet, or face, for reconstructive procedures.
For our design of experiment, we broke it into two different categories. The first one being biocompatibility. For biocompatibility, we tested for cytotoxicity, where we took the initial cell absorbance and final cell absorbance. For mechanical properties, we tested for degradation, where we had the initial mass of the substrate and the final mass of the substrate. And for tensile, we used the stress strain curve to locate the fracture stresses and strains for the different materials we created. For our preliminary methods for preliminary cytotoxicity testing, we fabricated 6 different substrates of varying materials in different colors, and we tested for whether the materials themselves were cytotoxic or if the artificial dye used for them was cytotoxic. We used a gray and black PLA, which is polylactic acid, using an FDM printer. We used purple and brown ABS on also an FDM printer, and then a carbon fiber nylon on an FDM printer but higher resolution, and an SG resin using an SLA printer. For our methods, we put the substrates into a falcon tube filled a third of the way with growth media and pipetted in 100 microliters of E. coli culture and placed it on an agitator rotating at 120 RPM. We measured the cell growth every 4 hours, 2 for once it started growing more. and we put it into a 96 well plate where we measured the absorbance post-experiment and examined just to see if there was any visible biofilm by the naked eye. Using the absorbance and time, we plotted a growth curve on MATLAB, which we analyzed into 3 different phases. We have the lag phase on the left side, the log in the middle, and the stationary phase on the right. What we saw was none of the materials were cytotoxic. The curves resembled a typical E. coli growth curve. However, the main change was in the initial lag phase, which was the time it took for it to start reaching its growth period. We continued our experiment further with the SG resin. Our method started by fabricating different materials. We chose to use a solid geometry and a scaffold geometry. We chose the scaffold geometry because it's commonly used in tissue engineering and it supports more cell proliferation. We use different ratios of agent nanoparticles and SG resin, so at 12%, 5%, 7%. So our process for making the SG resin with the agent nanoparticles was to use a stereolithography printer. Over here, it was Formlabs 2, and it works by curing. It uses light to solidify the resin, which is initially a liquid, through photopolymerization, and builds it layer by layer. So in making this making our substrates, we had to put in agent nanoparticles into the resin tank. We mixed it thoroughly as we could, and then set it to print. Post-print, we had to put it into an isopropyl bath for 15 minutes for 2 different ones, and then followed by UV, curing it under UV light. Until it's cured under UV light, the material is toxic. What we observed was, with the addition of the agent nanoparticles, the resin, which was initially clear, went to a more opaque white color, as you can see up there with the 5% ratio. For our first experiment, we were testing for biological responses, so we made a dish geometry with the SG resin, and we poured in 30 milliliters of white PD media, 1,000 microliters of yeast culture, and we, after setting that up, we breathe easy on top, so if there was any, to prevent any spillage and to allow the cells gas exchange. And we had it in an incubator set at 30 degrees Celsius, which we taped onto an agitator rotating at 70 RPM. And for the results, we saw that there was actually biofilm produced on the 4 sidewalls and the base, which was a positive result because it showed that there was an interaction between the material and the cells. For future work, we'd like to redo this experiment, but with Acetobacter xylem, and grow it on varying compositions of SG resin and agent nanoparticles. After we grow it on there, we'd like to measure the amount of cellulose that is secreted against the varying compositions and measure the adhesion under a microscope.
So for the next part of the experiment, we fabricated these dog bone shapes for tensile testing. They're made of the same materials, and then we submerged them in white PD media in petri dishes and pipetted in 1,500 microliters of yeast culture after vortexing them for 45 seconds to evenly disperse all the cells. Here are the results of some of our tensile tests. We have the SG resin without and with cell exposure to see if there was any differences. And then we have the 7% HA nanoparticle resin with and without cell exposure. And here we have the scaffold models where we had 5% HA, and we had to apply epoxy on the 2 ends of the dog bones to make sure it withstands the clamping force of the tensile test, and so the fracture occurs in the center region. And here are the results. The red line is the SG resin without any HA, so that was our control. As you can see, the HA nanoparticle specimens were weaker than the control, which about like 3 megapascals lower in tensile stress. And here we have the scaffold test results, where each of them were not significantly different based on the with or without cells, but they were weaker than the solid geometry, which we expected. So to test for cell adhesion, we designed a method where we used fluorescent microscopy and staining the yeast cells with chalcophore white, which is a fluorescent stain. So we first set up a positive control, which is just yeast and media on a slide, and we were able to see clusters of cells using bright field settings, and as well as the fluorescent filter. We could tell that the dye was working, but when we tried looking at the cells, at the actual resin that we expected to see cells on, we got that image under bright field settings. So there could potentially be clusters of cells in that picture, and to verify that we had to switch to fluorescent settings, and then we got a very poor quality image because of the light diffraction throughout the resin, so we couldn't really tell, there was too much interference to tell where the cells were. So to address this problem, we plan on smaller size specimens to reduce the amount of light diffraction and background interference, or try colorimetric stains instead of fluorescent stains, so we don't need fluorescent light filters.
For our mass results, for our SG resin by itself without nanoparticles post-experiment, we baked out our substrates in an oven at 120 degrees Fahrenheit for 30 minutes to remove any moisture from the media that was left over, and we wiped it down with ethanol. For the SG resin by itself, we saw a decrease in mass. However, for the SG resin with the HA nanoparticles, there was a slight increase in mass for both the solid and scaffold geometry. We think this could be credited towards, once we added the HA nanoparticles into the SG resin, it changed it might have made it more porous, allowing for more cells and the media to seep through the substrate. So when we baked it out, maybe the media didn't remove completely, or there's still some dead cells inside. To test this hypothesis for future works, we could break the substrate of varying parts and then examine it under a microscope to see if there are any cells that remained. We can also look at the porosity of the material under the microscope, or we can increase the bake-out times to see whether if it's just media left over and the water evaporates for either 1 hour, 1.5 hours, and 2 hours.
So in conclusion, we think that the SG resin with HA nanoparticles produced by SLA printing is a suitable substrate for interfacial biomaterials. While we have not actually have a quantitative measure of adhesion, we were able to see biofilm on all of the samples, which is a good sign. We plan to develop a material through the interaction of biological cells and substrates, and to test the material for unique properties, and this project will serve as a foundation for future research. So in the future, we will repeat the cell adhesion test with a revised method, and the experiment will be repeated using Acetobacter in place of the yeast to produce the bacterial cellulose. And finally, the resulting interfacial material, which would be the polymer plus cellulose, would be tested further for applications in bone screws.
For our cost analysis, we incorporated the materials that were purchased that weren't already readily available at NASA. So total came up to a little over 1,000. This isn't including the SLA printers or the machine shops and everything else we used. We'd like to acknowledge our industry advisor, Dr. Diana Gentry, and our SJSU advisor, Dr. Selvaduray, for the guidance and support they provided throughout this project. So our references, any questions?
So, could you go to your tensile tests? The actual images, yeah. You were saying something like you're trying to make them fracture in the middle.
Yeah.
It doesn't look like they fractured in the middle.
That was for the scaffold, which is why we added epoxy, because we didn't want the clamping force to cause a fracture there. So we just wanted to ensure that the strongest points are on the end and the weakest are on the center, so we can gauge that it came from.
Yeah, but it still looks like, it doesn't look like it fractured in the center
Yeah.
for all of them. So even these ones and those ones.
Yeah.
So it might be best to maybe consult with someone in materials engineering or something, because the technique for holding the samples might have been improper, leading them to fracture, and that could impact the quality of your results there.
Okay.
Yeah.
Did you check if there was any interfacial material with any method?
We didn't. We weren't expecting the yeast to do anything like that because the yeast cells were basically the first step in using other cells that would create an interfacial substance like cellulose. So we're making sure.
We wanted to validate it with something we had readily available and we could culture easily, just to make sure that our method and process do work. So when we go on to use Acetobacter, we'll have that at least worked out with like more complex cells.
So you want to create interfacial material, and then you're using this just as a proof of concept that you can actually grow anything on the surface?
More so that we were able to get a response with the yeast cells, because we saw the biofilm here, so that was positive, saying that because we did try with different materials like PLA, and when we used the PLA for a dish, there actually wasn't any biofilm visibly available, any biofilm that was produced inside the dish, but with the SG resin, there actually was biofilm. And because with the interaction and it was formed, it's kind of supports, we can move forward with it with Acetobacter and something else.
You mentioned something about shape memory alloy with PLA. How does that come about?
So that was actually how we decided to use hydroxyapatite, but we haven't tested it with the resin that we're using right now. For the PLA, we would have to basically melt the polymer and then mix in the hydroxyapatite and then extrude it again. But we decided to use the resin because it was easier to mix because it's already a liquid initially.
We did actually try mixing the PLA with other filaments, so later on we could add the hydroxyapatite because it was a little more expensive. But we didn't have a filament extruder available at NASA, and they're really expensive to buy, so we used a cheaper one, and we were having problems getting it to extrude uniformly where we could use it in the 3D printers, but we're thinking of molding for the future tests because we couldn't get the extruder to work yet.
Why did you use HA in nanoparticles?
Because it's known to increase bioactivity, so you would have cells grow at a faster rate and they would react faster, so like in theory you would be able to create more cellulose.
So that is kind of serving a similar purpose to hydroxyapatite in this case? Or
You mean the PLA compared to the resin?
right.
Yeah.
For shape memory, is it because of a difference in glass transition temperature between the polymer and the hydroxyapatite? And which one changes shape and comes back?
I think it was, so when they're together, when the hydroxyapatite is mixed into the PLA, that was when the shape memory effect was observed in the study we looked at.
All right, thank you very much. Oh, sorry, any other questions? Okay. I guess you guys can go ahead. Name, you go ahead.